Okay, great. All right, so today we are going to continue on with electrostatic potential energy. Last time what we did is we talked about how to calculate the electrostatic potential energy. Well, we talked first about what electrostatic potential energy is. We spent about half the lecture on that. And then the second half of the lecture, I showed you how to calculate the electrostatic potential energy due to discrete charges. Does anyone remember what a discrete charge is? Just go ahead and drop it in the window if you could. What is a discrete charge? I see Bilal is typing. Impulsive charge. Okay. A charge with a quantifiable value. Yeah, those are both reasonable definitions. So discrete charge means essentially like you have a fixed amount of charge. As Joseph, I think that's a good definition. A fixed amount of charge in a specific location. We're going to talk today about charge densities and how to calculate electric fields from distributions of charges. Okay, and then as I said, the second half of class we're going to cover how to do COMSOL simulations. And if I can just, I'll just jump ahead to that so you can see what that's going to look like. So this is going to be something that we're going to be doing today. How to use COMSOL to solve a simple situation of a quadrupole, very similar to the Python example that we did the other day, but how we can use this COMSOL software, finite element software, to solve for the electric fields. And I think you'll find that pretty interesting. So let's back up for a second. Quick recap of what we did last time. We talked about the mechanical versus electrical work. In both cases, the work is given in joules. We talked about the work required to move a single charge. That was an example problem. We talked about potential energy and how you have gravitational and electrostatic potential energy and how they are similar to each other and how they are different. Okay? We talked about deriving the potential energy using the concept of work. And what we found is that the potential energy of the mechanical system is mgh. This is where you have a ball at a height above, at some height above the surface of the Earth. And then in the electrostatic system, the work is equal to the voltage times the amount of charge. We got into the definition of what electrostatic potential is, and there's a differential form that you saw down here and an integral form. And then we got into the electrostatic potential difference between 2 points. And we said, how do you calculate the potential difference between 2 points if you know the electric field? And so one of the important points we made here is that we said is path independent. You can do a line integral from P1 to P2, and it could be a straight line like this, or it could be a curvy line like this. It could be any arbitrary line that you choose, but the difference in potential that you will calculate is going to be the same regardless of which path you integrate over. We did an example of that where we found the electrostatic potential difference between 2 points, and that's on the one node. The electrostatic potential from a single charge we showed at the end of class last time. What we did here was we derived a formula for the electrostatic potential due to a single discrete charge, so a single charge Q. And the observation point where we're measuring that potential is a distance r away from that. So we came up with a simple relationship, Q over 4 pi epsilon r. So if our observation point is a distance r away from the charge, and the charge Q, then the potential at that point is going to be given by this equation. Then we said, okay, from a single charge, we know how to calculate the voltage due to a single charge. What if you have multiple charges? And we said, okay, here's a simple example of a dipole where you have 2 charges, and you use the principle of superposition, and you say, what is the electrostatic potential due to charge number 1? And what is the electrostatic potential due to charge number 2? And you just add them together. So it becomes very straightforward to be able to calculate the electrostatic potentials due to multiple discrete charges. And so as you can see here, we're just adding up Q over 4 pi epsilon 0 R1. This is the voltage due to charge 1. And then the second term here, which would be negative Q over 4 pi epsilon R2, would be the electrostatic potential due to charge 2. So you literally can just add them up. Everything else here is just mathematical simplifications for specifically for the electrostatic dipole case. Once you know what the electrostatic potential field is, if you have a relationship for that, you can take the gradient of that and then find the electric field. And that's what we showed at the end of class last time. So what we're going to do today, is we're going to show you how to, let's back up. Oh, sorry. Forward. Okay, today we are going to show you how to calculate the voltage due to not just discrete charges, 1, 2, 3, or 4, but if you have a continuous distribution of charges. So the problems that we're doing here, you can see that they involve integrals, and they're going to be similar to the types of problems that you have done previously for electric fields. And we're just going to show you how to do this with voltage, calculating voltages instead of electric fields. And what you're going to find is this method is often easier than calculating electric field. And the reason why is because if you remember, electric fields were a vector quantity. We had to integrate a vector relationship, a vector field, and we had to find the components in the x and y or the theta directions in multiple directions. You'll notice here these integrals are just scalar integrals. They're not vector integrals, right? So I would say that these are easier to work with than the electric fields. All right, so let's get right to it. So we'll go right into an example here. So we have an example where we have a disk of charge. So suppose we have a disk with radius b and uniform charge density rho sub s. Calculate the electric potential at a point on the z-axis. Okay, so the strategy for solving this problem is going to be first to draw the geometry. We always start our problems with that. The second step is going to be to determine what type of integral we have, a line or surface or volume. And then we figure out the limits of integration. And then, if we look at these equations here, we look at, in these equations, there's dV, ds, and dl. So we have to figure out, in each one of these cases, we have to figure out what rho is, we have to figure out what r is, and then we have to figure out what dV, ds, or dl is, depending on the type of problem that we're working with. Then we also have to figure out our limits of integration, whether we're doing a volume, surface, or line integral. And then the last step is to actually do the integral. So the reason I break it up like this is because, so you're very, very clear about each part of the integral and that you really understand where each one of the parts are coming from. So we're going to go through each one of those steps. That's 1 through 5. And then step 6 is just to do the actual integral. This is the answer here, so hopefully we'll get to this answer at the end. And our objective is to is really to show the process. Like I said, on your tests, I'm more interested in your process than I am in the final answer. I want to see that you know the steps of how to solve the problem, how to attack the problem. Okay, so the first thing we'll do is just draw the problem. So let me go to my PowerPoint here. Sorry, not my PowerPoint. OneNote. Give this a second. All right. So what we're given here is we are told that there is a disk of charge with radius b and the uniform charge density rho sub s. And we're asked to calculate an electric potential at a point on the z-axis. So here's how we're going to draw the problem. All right, so here's my x, y, and z axis. The x-axis, of course, is this one here. So let's draw a disk of charge. So imagine that we have disk here like this. Of course, my drawing is terrible. That's a little better. Okay, so we have a disk, and this disk, it has a charge density rho sub s. Okay, that's the amount of charge that we have on there. Now we have a point, our observation point is on the z-axis. So let's draw our observation point up here. There we go. So observation point P over here. And this is at some height. The coordinates for this point P is 0, 0, h. Okay, and we are asked to find the potential at this point P on the z-axis. At a height, it's separated by this disk of charge by a height h. So let's just draw that specifically in there. Okay, the distance here is h. Okay, so let me just so the first question is, what type of integral do we have? So this is something that let's just go ahead and have someone answer that on the public chat. So is this going to be a line integral, a surface integral, or a volume integral? Okay, Bilal, thank you. All right, great. We have agreement. It's a surface integral. So why is it going to be the surface integral? This may be obvious to many of you, but let's just make sure that we know how to look for the clues. How do we know that it's a surface integral? Okay, rho sub s, yep, versus rho sub L or rho sub V, if you had a line or volume integral. And a disk of charge is essentially a two-dimensional object, right? If we had a volume of charge, that would be three-dimensional. Okay, so we know that this is going to be a surface integral. Now the next part is, what are the limits of integration? So what I'm going to do here is I'm going to show you this image real quick. So this is going to be the disk of charge. Okay, and I'm also going to remind you of what the equation is. This is the equation for surface charge distribution. So you can see that we have two integrals that are going to be done. So where do we want to integrate to be able to integrate over that disk of charge? So I'm just going to make this a polling question. First question is, what are the limits of integration? And I'm just going to put that poll up here. So there's several choices. Looks like there's, okay, so I need to actually make a custom poll here. No. Okay, there's only A, B, C, D, E. And you can see here that there's A, B, C, D, E, F choices. So just cross off F. That's not going to be one of your options, and it's not one of the correct answers here. So we'll make it easier for you. This is not one of the answers. So go ahead and take a second to think about this. What is going to be our limits of integration? And if you have questions, always feel free to put the questions out on the public chat. Okay, see, we have one. Can I see it again? Of course. Yeah. Here we go. This is what the disk looks like. Yep. So let me go back to the different options. So if we want to get a disk, what are the two variables we're going to integrate to get a disk? The surface of a disk. Okay. Still waiting for a few more people here. Okay, a few more people. Let's get one more person responding here, and then we'll continue. Okay. All right, so let me share the results with you. One person had a B, 11 people had C, 5 people had D, 5 people had E. So close to half of you put C, and that is the correct answer. So good. Oops. So why is the limits of integration 0 to 1 and 0 to 2 pi? Well, let's start with no one put A, so we don't have to worry about that one. Theta equals 0 to pi and phi equals 0 to 2 pi. This answer here, theta and phi would be the cylindrical coordinate system. I'm sorry, the spherical coordinate system, and we are in the cylindrical coordinate system, so that's why this would not be the correct answer. C is the correct answer. So if you think about the disk that we're looking at, if we look at the three variables r, theta, and phi. So we have three variables r, phi, and z. We're in the cylindrical coordinate system. Whenever you're working with disks and cylinders, the cylindrical coordinate system is the easiest one to use. So our r is going to go from 0 to 1. Okay, so all values of r between 0 and 1 are included in this disk. And if you think about the theta variable, which goes around like this, all values between 0 and 2 pi are part of that. So you get this entire disk like that. That's why C is the correct answer. D, R is going from 0 to B. And then phi is going from 0 to 2 pi. Actually, hold on. Actually, hold on. We have to fix something. It's actually the radius of this disk is B. So the radius of the disk is B, so I apologize. The correct answer is actually, it's D. I read that wrong, I'm sorry. This is the correct answer. C is not the correct answer. Why? Because this is going from r equals 0 to 1. And the radius of our disk is equal to B, so we want to be going from 0 to B. Okay, so let's just cross that out to make sure that we're all clear on that. Our phi is going from 0 to 2 pi. And E is, here we're integrating three different variables, and that's, of course, we don't want to do that. We're integrating a surface, so we're only integrating two variables. If you're ever asked to integrate a line, you're only going to be integrating a single variable. Integrating a surface means integrating two variables. Integrating a volume means you're integrating three variables. So that's another clue you can think about. Okay, all right, thanks for your input on that. Oh, I see there's some questions. I thought, oh, John is saying, I thought B equals 1. Now, Abdullah said we were given B for radius. Yeah, thank you. Thank you guys for catching that. Yep, thank you for that. Appreciate it. Okay, so let us now go to the next part of the problem. We figured out the limits of integration. So limits of integration here is going from r equals 0 to B, and then phi equals 0 to 2 pi. That way we get the entire amount of charge there. And the next step is to find ds, and then find r, and then integrate. So I'm just going to go ahead and do this problem on here. So I'm going to just write this down again. So we drew the geometry. We know it's a line integral, so the limits of integration, this is step 3. So r is going to be from 0 to b, and then phi is going from 0 to 2 pi. Okay. Next step is to find ds. And ds, we are in a cylindrical coordinate system, so ds is equal to r dr d theta. Now, how did I come up with this? We look at our the variables that we're going to integrate. Whenever we integrate through r, our differential length element is dr. Whenever we integrate phi, our differential length element is r d phi. So our ds, considering that we're integrating both of these variables, our ds is going to be r, you have your dr here, and multiply that by r d phi, and that's how you get this right here. The next question, and this is going to be a question for all of you, is what is r? Okay, now the hint I'm going to give you is, well, you have to imagine that you are at some point, let's say you're at some arbitrary point here. Okay, imagine that you're at some arbitrary point on this disk, okay? I drew the point. It happens to be on the y-axis. It doesn't have to be. It could be any point in this disk. Okay. Now, what I'd like you to do, what you're interested in finding here, is for some point r phi, and of course your z is going to be equal to 0. What's the distance to the observation point? The observation point up here. Okay, so I'm going to go ahead and let you, you can calculate it while this image is up on the screen. Use a sheet of paper, and then in a minute or so, I'm going to actually switch back and forth so that you can see what your options are as well. So yeah, let me just start the poll here. So you can see your polling question up there, and there we go. So do this. All right. Okay, I'll give you a minute or so to take a look at it. So let's go back to the image here. So again, we're at some arbitrary point on the disk, and we want to find the distance from that point to the observation point. So still waiting on a few people here. So even if we don't have the entire class, I'd like to get a few more people here. And even if you're incorrect, it's no problem. But the goal is to get everyone actively participating. All right, we have 19 responses. So let's wait for, there we go. All right, so we got 20 responses. 21 folks indicated B, 22, and then 1 indicated C. So that's great. Song is asking what is r again. R is the distance. R is the distance between 2 points. So let me jot it down here. This is r. That's the r that we're trying to calculate. Can you go back to the choices? Yeah, these are the choices. And so let me share the polling results with you. Most of you put B, 92% of you. That's great. That's what we're looking for. And I can also see that somebody put it on the public chat, which is fine. So thanks, Hamza. Okay, that might explain. All right. So the correct answer here is B. All right, and I'll just show you really quickly how to calculate that. So it's just using, of course, just using the Pythagorean theorem here. You're at a height. The height here is equal to h. Let me just delete this. It's a little bit easier to see. The distance here is r, and this is the magnitude is r is equal to the square root of r squared plus h squared. Right. So I meant B, is r a hypotenuse for the right triangle? Yes, it is. So r is equal to r squared plus h squared. Correct. So let's write that down. So our r is equal to the square root of r squared plus h squared. Okay, so this is the distance from the observation point to one of the charges on the disk, because we're trying to add up all the contributions of those charges, right? All right, so the next part of the problem, look at our strategy, sorry. We found ds, we found dr, and now we just integrate to find the voltage. All right, so now we are going to integrate. Say v is equal to 1 over 4 pi epsilon. The integral, double integral of rho s over r ds. Now, we've already figured out all the major parts of this, so that makes our problem easier now. So it becomes 1 over 4 pi epsilon. And we can move the rho s out because the rho s happens to be constant in this problem. It's a disk of uniform charge. And now we can look at our limits of integration. So we said phi is going to go from 0 to 2 pi. And our disk radius is going to go from r equals 0 to r equals b. All right, let's make this a little bit larger here. And we determined what r is. So we have 1 over r here that we need to put. R is equal to the square root of r squared plus h squared. And then ds, this part here, ds we found is r dr d phi. All right, so you set up your integral here. If this was a test, if this was on a test, like if you set up the integral properly with the proper limits of integration, you'll get most of the points. Okay, that's mainly what I'm looking for. The rest is just math, so we can just do this real quick. Rho s over 4 pi epsilon. Now, in this type of situation, we have this function of r that you see here. And then we also have a function of phi. So when you have a function of r here and there's no phi in here, that means it's, the functions are independent, so you can separate them out as we've done before. So we can just do phi equals 0 to 2 pi, and d phi goes here, separate it out. If r equals 0 to b, r dr over square root of r squared plus h squared. Okay, rho s over 4 pi epsilon. This part here becomes 2 pi. All right, the integral of d phi is phi, and you evaluate that from 0 to 2 pi, and that's how you get your 2 pi here. Now, the way you evaluate this part here is that this is in the form it's r squared plus h squared. So imagine that we're going to put this in the form of du over u. So our u is equal to r squared plus h squared. Du is equal to 2r dr. So the strategy that we used here, if you remember from calculus, is that you notice that, oh, this is this looks like it's in a particular form. Now you could look this up in an integral table too, but I'm just reminding you from calculus, is that you see this r squared plus h squared on the bottom, and then on the top you see that this is r is a derivative, form of the derivative of this, of what's on the bottom of the fraction there. So we define this as a variable u equals r squared plus h squared, and then the derivative of this u is going to be 2r dr, take the derivative of this, and so you can put this, you can put this in the form of 1/2 u, I'm sorry, let me just be totally clear here with this. So r dr is equal to 1/2 du so this equation can be put in the form of 1/2 u to the negative 1/2 du. All right, and the integral of this is u to the 1/2. All right, the integral of u to the negative 1/2 is 1/2, and then you have to divide what's out here by the 1/2, so you get u. If you don't believe me, you can just take the derivative of this and you will find this. All right, so the integral is u to the 1/2. So we're going to substitute in the u equals 1/2. It's r squared plus h squared, square root of h squared from, and it's evaluated from 0, oops, let me rewrite this to make it clear. So this is going to be the square root of r squared plus h squared, evaluated from r equals 0 to r equals b. All right, everybody with me here? Give me a thumbs up if you are. Okay, if there's any questions, please do let me know. So this is going to be b squared plus h squared minus the square root of h squared. All right, so we get rho s over 2 epsilon All right, actually, we need to fix something here. Hold on. So we did a change of variables, right? So we changed this this equation over to a form u. Okay, and I think this is something I didn't catch earlier. So there's always a lot of math to do in these problems. So when r equals 0, we have to look at our limits of integration. So when our r is equal to 0, our u is equal to 0 squared plus h squared, or u is equal to h squared. And so when r is equal to b, u is equal to R is equal to B. This is equal to U squared. I'm sorry. B squared plus H squared. Okay, so when we evaluate this, you know, we evaluated this as the integral was U to the 1/2. So U to the 1/2 evaluated from R equals 0 to R equals B. So we have to transfer that over to U, the variable U. So when R is equal to 0, U is equal to H squared. And then when R is equal to B, U is equal to B squared plus H squared. So we actually have to substitute that in there. So let's do B squared plus H squared, square root of B squared plus H squared minus the square root of H squared. All right, that's the proper way to do this. Rho S over 2 epsilon, and this will be the square root of B squared plus H squared minus H. Okay, so that is our the electrostatic potential at some height h above, on the z-axis. All right, so there's some math involved here. I hope that if this stuff is unclear to you, you can review concepts of integration when you're doing a change of variables. That's what this is called. We did a change of variables here. And remember, you can also use integral tables. You know, this is probably you could probably find this in any integral table that's available to you. Okay, this is not a math class, so I'm not going to be assigning most of the points based on how well you integrate. Most of the points that I care about is how you set up the problem. Do you understand the limits of integration? Do you understand how to calculate these different parts of it and set up the problem? Okay? All right, so B squared plus H squared minus H. So this should be B squared H squared, and this will be minus H. Okay, assuming that you are at a height h on the z-axis. All right, so let me ask you, any questions on that then? Any questions on this problem? Okay, all right. Where did my mouse go? Okay. All right, the next one we're going to do is a ring of charge. And the reason we're doing such a similar problem to what we just did earlier is because this is a problem that you saw previously. If you remember, like in the previous lectures, we actually covered how to calculate the electric field due to a ring of charge. It's been a while since we did this. We did this before spring break. So you may not recall, but I'll just remind you that it was a multi-step problem, and there's a lot of parts to it that we had to figure out. Maybe if I have the notes here, I can show you. Okay, these are some other examples here, it looks like. All right, I'll just mention that when you find the electric field using the standard methods, you have to account for these vector quantities. Okay, the fact that you could actually have an electric field in the z direction and the y hat direction. So when you're doing integrals with vector quantities, it becomes kind of a pain. When you're asked to find electrostatic potential, potential is a scalar quantity, so the problem becomes a little bit easier to do. So if you're trying to find the electric field, you could actually first find the scalar potential and then find the electric field by taking the gradient of the electrostatic potential. So that's another strategy for problem solving here. So what I'm going to do is now I'm going to walk you through how to do the line of charge problem using this electrostatic potential approach. All right, if you recall, last time we found, this was again before spring break, we found that the electric field is equal to rho L over 2 epsilon BH over B squared plus H squared to the power of 3 halves. And what we're going to find now is that the voltage is going to be equal to rho L over 2 epsilon B over square root of B squared plus Z squared. Okay, Z squared and Z is like whatever the height is, so we can actually say H here, indicate H representing the height above the ring of charge. Okay, so really quickly, I don't have any poll questions for this, but do we have, you know, are we going to be doing a line, surface, or volume integral here? Just go ahead and put it out on the public chat. Okay, great. Yep, they are all line integrals, correct? You see this rho L here. And let's find the scalar potential. Let's go through the different steps of the problem here. So I'm going to open up a new window. Yeah. Find it easier. Okay. So we're going to start by drawing. That's the first step of the problem. Draw it. Always makes your life a little bit easier. All right, so we have a ring of charge. So I'm going to draw it in red. So you can easily, oh, no, that's not what I want. Yeah. All right, so you have a ring of charge here, whereas before you had a disk of charge. Now you just have a ring of charge. All right, so just imagine that you have a bunch of charges in a ring like this. And that charge density is given by rho sub L, units in coulombs per meter. So I'm going to go through this problem a little bit faster here. So we are at an observation point P that's at a location 0, 0, Z, or H, let's say, on this axis. All right, cylindrical coordinates. So the first thing we figured out was that we're in the cylindrical coordinate system and we're doing a line of charge. And so let's first figure out our limits of integration. Make this smaller. There we go. So the limits of integration, this would be step 3. It's not. There we go. All right, can someone help me out with this? What are our limits of integration in this case? How many variables are we going to integrate? Let's start with that. 1, right? And what is that variable going to be, and what are the limits going to be? Asang is saying the limits are going to be from 0 to b. Bilal is saying the phi is going to go from 0 to 2 pi. Puja is also saying 0 to 2 pi. Okay, seems like we have a lot of folks saying 0 to 2 pi. Yeah, so this is actually correct. So the limits of integration, the phi is going to go from 0 to 2 pi. Okay. If, let's say, if we were integrating a line of charge and that line of charge happened to look like this, if our line of charge happened to go like this, from the origin out to some point r, in that case, we would integrate r from 0 to b. But yeah, exactly. That's right, Song. It's 0 to 2 pi because we're going around the circle. Exactly. You got it. You got it. Okay. So let me just, how do I undo your, there we go. All right, we're integrating around the charge. All right, the next step is to find ds, or in our case, it's going to be dl, because in this problem, we're doing a line integral. And so we have this variable phi. Whenever we have a variable phi, the associated differential length is r d phi. So our dl is going to be equal to r d phi. The next step is to find what is the distance. All right, so again, we're going to go through the same process we did before. We're at some observation point P, and we're at some point along the line. So we can draw a right triangle here like this. And we know that this is at a height h, and this is at a distance b. The ring of charge has a radius b, and so this is equal to h squared plus b squared. So that is our r. Right? And the next step is going to be to set up the line integral. We'll do step 6 here. Voltage is equal to 1 over 4 pi epsilon. Integral, we're just doing a single integral in this case, rho L over R, and this is going to be dl, integrating a scalar quantity. All right, so we can start plugging some stuff in. 4 pi epsilon. Our integral is going to go from 0 to 2 pi, right, because we figured that out. Our r is h squared plus b squared. And our rho L is going to go outside here like this because that's actually a constant. Now, in some of the problems I give you, rho L may not be, it may actually be a function of phi or something like that. So keep that in mind. We're able to bring it out in this problem because it's a constant, it's fixed. It does not change as a function of phi. We're also going to put in our dl here now. Now keep in mind this dl is equal to r d phi. Now in this problem, we're integrating along the circle here, so this r is going to equal to b, right? Everywhere on this ring, the radius is equal to b. So this will just be b d phi. So that's why we could put here, we could put b times d phi. And since b is a constant, this can also come out. All right, now let's look at our integral here. So this is actually fairly simple here because you can see that none of these variables, 1, h, b, none of these variables change as a function of phi. So this whole thing is a constant here. This whole thing can come out of the integral. And we're just left with the integral from 0 to 2 pi of d phi. So, and that is equal to just 2 pi. So we get rho L over 4 pi epsilon 1, we'll make this b over h squared plus b squared times the integral from 0 to 2 pi. Uh-oh. Did I lose my screen share? All right, you should be able to see my screen now. Okay. All right. Yeah, you can see my screen. Good. And this integral from 0 to 2 pi of d phi is just equal to 2 pi, like this. And so the final answer then becomes rho L over 2 epsilon times b over b squared plus a squared. Right? So this is our final answer. All right. So quickly went through this problem. Now our next step, this problem is asking us to go one step further. There we go. Hide this. This problem is asking us to go one step further and then calculate the electric field using E equals the gradient of V. All right. So as you saw previously, before spring break, we solved for the electric field directly using the Coulomb's law integration approach, which I call the brute force approach. Now what we're doing here, we find the scalar potential first, and then we just find the gradient of the electric field to find the electric field. Now, one point I want to make, very important point, is that we are finding the electric field on the z-axis, right? These formulas apply if you're at a point on the z-axis. If you're not on the z-axis, this whole derivation or this whole calculation that we're doing doesn't apply, right? Just want to point that out. Okay, so when we're doing this, when we're saying we're finding the electric field, we are finding the electric field just along the z-axis. So that means r is equal to 0. I'll just make a point on here, on z-axis. So the r equals 0, and z is at some fixed value h. Okay, and when you're at r equals 0, the phi is irrelevant. I'll just note that down. Phi is only means something if you're not at r equals 0. All right. Questions so far? Thumbs up if you're with me here, and put out any questions if you are. Great. Okay. Thanks, everyone. All right. So we're going to find the electric field as the negative gradient of the potential V. All right. And the way we do that, we've already talked about how we can calculate gradients. If we look back on our charts, remember, we're trying to find the gradient in a cylindrical coordinate system. And in the cylindrical coordinate system, let me just write down the formulas from our vector math chapter. It's equal to dv dr times r hat. Remember, in the cylindrical coordinate system, you have to be careful. And you have to add these extra terms, 1 over r dv d phi times phi hat. And then the last term is dv dz times z hat. All right. So this was all just looked up on a table here. Now I want to point out that these first two terms are just equal to 0. And the reason that it's equal to 0 is because the r is equal to 0, and then our dv d phi is irrelevant, right? There's no change in voltage as we change phi, because phi is irrelevant in this at r equals 0. So this term goes away, and dv dr also goes away because r is a constant. So dv dr has to be 0. So we're only looking at this last term here. It makes our problem a little bit easier to do. So it's just equal to dv dz times z hat. All right, and so we can do this as z hat, and we're going to take the derivative with respect to z, so d dz, of the electric field that we found. We just substitute rho L over 2 epsilon b over the square root of b squared. Now, This is something that you have to be careful about here. So this, remember, this is giving us, this is the scalar potential at some height at z equals h, right? So this h represents the the point on the z-axis. So when we're trying to find the gradient, we have to take the derivative of the electrostatic potential with respect to z, right? This h represents a coordinate on the z-axis. So we actually have to put z here. Okay. Right, because we're trying to find the derivative of the electrostatic potential with respect to where we are on the z-axis. So z is a variable here. Right, we have to find, when we find the derivative of this function, you see that b is at the top, but you have the z at the bottom. So when you find the derivative of that, this is b squared plus z squared. This is b squared plus z squared to the negative 1/2, right? With the square root, it's on the denominator. So the derivative of that is going to be negative 3/2, and then you also have to take a 2z out in the front. So this is going to be z hat 2z rho L over 2 epsilon, and we'll have b over, I'm sorry, rho L b. Let me clean this up a little bit. This is getting a little messy. Is going to be rho L times b over 2 epsilon times z. The 2 will go away. Right, because we have to brought out the 2z, and then there's a 2 in the denominator, so the 2 goes away, and we're left with b squared plus z squared to the power of 3/2. Okay, so this is our relationship for the electric field. There's a lot of math that we had to do to figure that out. We figured it out. And you'll see that this result actually matches the result that we found earlier using the longer brute force method. Okay, this is in a slightly different form, but it's basically the same. Okay, now, any questions on this? Falak, should z hat be negative? Okay, where are you guys saying? Are you talking about in this electric field formula here? Okay, let me check my answer. Yes, this is negative 3/2. Thank you. Important here. The negative 3/2. Thank you for that correction, Falak. Appreciate it. All right, so we've solved 2 problems now using this type of approach. All right, so what I'm going to do now is we're going to switch gears now. We figured out how to solve this type of electrostatic problem where we're looking for the electrostatic potential due to charge distributions. We did a surface integral example, and we did a line integral example. Okay, so just bear with me here. I'm actually going to stop the recording for a second and wait